We've had some questions about the equations of motion and where they come from. So I'm going to try using some graphs to give you maybe a little bit more of an intuitive understanding. Your book talks about this a little bit, but I think some people thought it wasn't very clear, so I'll expand on that a bit. Okay, so we'll start with the simplest situation. So we'll say that the acceleration is 0 at all times, right? We'll also say that the velocity is going to be 0 through the whole range of motion. So what does that mean for the position? Well, if something has no velocity, it's not moving, right? So that means if it's at this position x, that at some time later it'll still be at x, a little while later it'll still be at that same position, and so everywhere it's at this same position. We'll label it x0. So this is obviously the simplest because there really is no motion. We'll look at another case now where, again, there's no acceleration. But now we'll say that the velocity is constant in time. So again, this means that at each time, the velocity is unchanged. So now what does that do for the position? Well, we know for velocity, our definition of velocity is that it's the change in position over the change in time. So rearranging this, the change in position equals the velocity times the change in time. So in other words, if we start at some position x0, then its position at any other time is going to be the velocity times that time. In other words, it's the area under this velocity curve, right? Because this is the change in, this is the velocity, and this is the time, or change in time. But now this is the change in position, right? In other words, x minus x0 is v delta t. Now since v is constant in this case, right, then this also means that delta x over delta t is constant, right? In other words, the change in x, we say delta x, and the change in time is constant, so we have a straight line here, and that gives us our graph for x, right? So it doesn't matter where we started in, this gives us the change in x. So notice, going back to our equation up here, we see that if we just pull the x0 over, we get x equals x0 plus vt. So we're partway to our x equation of motion. So now let's look at another case. Now let's look at the case where the acceleration is constant in time. Now using the same argument that we just used for velocity, right? Because similarly, we know that acceleration is a change in velocity over the change in time, which is constant, which means the change in velocity is equal to the acceleration times the change in time. So without bothering to go through kind of a more detailed description, we know that this area, right, a times delta t is the change in velocity. So that means now if we started at some v0, we would have a constant changing velocity, right? This is delta v, this is delta t. But now we have our velocity equation of motion from this, right? V minus v0 is equal to at, so v equals v0 plus at. So that's one way that you can think about where this equation comes from. Okay, now what about x? So for x, it's a little bit complicated because v is changing in time now, right? So now delta x over delta t isn't constant. Okay, so what is it doing? Well, in time, v is increasing. So let's say we split this up into a bunch of small time intervals, right? And so each one of these is a small delta t, right? Well, if v is increasing and delta t is the same, that means that the change in x must be increasing. In other words, if we start at some position x0, then in each time step delta t, we're getting steeper and steeper. And so essentially you get a parabolic curve like this for x. So we expect this to be something that looks like time squared, because that's the equation for a parabola. All right, and now we can go back and look and see if that makes sense. So if we look back at our area here in V, right, this is V0 times delta t. This area, right, so knowing here that this is going to be a times t, right, and that's equal to delta v. So this is a t, this is t. So so now the portion right here, this is going to be 1/2 at squared, right? Because if we had this full rectangle, this would be at times t, but we only have half of it, right? That's shaded that's in the shaded region, so that's 1/2 at squared. And again, using what we said earlier, since x is just the area under the curve, in this case that must mean that x, the change in x, right, is going to be v0t plus 1/2 at squared, or in other words, x minus x0 is v0t plus 1/2 at squared, which means x equals v0t plus 1/2 at squared. And so that's where this formula really comes from. And so now we have really the two equations that we need to describe motion under constant acceleration, right? We have our equation for position, and we have our equation for velocity.